Oh, IFL 2020, the new text adventure game. Let's see. You have some free time and you feel restless. Okay, so I feel restless, so that means I'm not satisfied with the outcome yet. So let's try something. What if I submit an abstract to the IFL? Yeah, let's try that. Okay, so it seems that the outcome depends on what kind of abstract it is. So let's see what happens afterwards. What if after I submit the abstract, I give a talk? Okay, so it seems that if the talk is interesting, it's going to be a success. So let's see, can we come up with a sequence of commands that would give us a satisfying end result? Yeah, I think we can. Yes, if I submit a good abstract to the IFL, and then the proposal is accepted, and then I give an interesting talk, then it's a success, and I can be satisfied with the result. So maybe I should get to it instead of playing text adventure games. Yeah, hi, I'm Gergo Erdi, and this is going to be a talk about an adventure in symbolic execution. And as we all know, the A in IFL stands for applications, so this is going to be an application talk. In fact, this is going to be an experience report of retrofitting symbolic execution into a generic purpose functional programming language. So, first some background information. So, interactive fiction is a kind of game where there is a textual back and forth between a user and a computer, and the computer usually simulates some kind of external world. And adventure games in particular are a subset of interactive fiction which are proper games in the sense that they have a well-defined win state. So for example, the IFL 2020 game had this well-defined win state of giving a successful talk. So because of this, unwinnable games are faulty because they're only going to frustrate the players. So that's what we are going to try to check whether games are winnable or not. So under the hood, text adventure games are usually implemented by having an interpreter for a whole class of games, like games from one company or games that use the same technology. And then individual games are just input data to this interpreter. So in this particular talk, we're going to be looking at the games from Scott Adams, unrelated to the Dilbert comic creator, who created his text adventure games at the late 70s, early 80s on the home computers of the time. So these were quite restricted systems, and his text adventure games were like small versions of the big adventure games that ran on the university mainframes of the time. So the inspiration for this talk came from Martin Lester's talk at the workshop on program transformation for evaluation, where he presented his work in this area. So what he did is that he took Scott Free, which is a off-the-shelf game interpreter for Scott Adams adventure games. So it's written in C, and it's decades old. And then he started modifying it. I mean, Martin started modifying Scott Free so that it could be passed to compiler that takes C code and turns it into SMT problems. So this required manually partially evaluating the game. So basically, for a given game data, he replaced the code that parses the game data with just static data, which is the internal representation of Scott Free for that particular game. And then, the game had lots of infinite loops because like a whole game itself is like an infinite loop of getting an input from the user and then reacting to it. So that one had to be, all of these infinite loops had to be replaced with bounded loops. And then with these modifications, SymCC, which is again an off-the-shelf thing, it's a program to translate C to SMT problems, was able to turn it into a format that could be passed to an SMT solver, Z3 in this case, and then this could be used to find solutions for the given text adventure game. So basically, it would be checking if the game is winnable by looking for a solution. And so my approach is going to be slightly different. So I'm going to try to do this with bubblegum and duct tape and just trying to hack together something that is not based on something as large as SymCC. Instead, I'm going to write an idiomatic Haskell interpreter that does concrete evaluation, and then I'm going to change it just so to use symbolic values. And so part of this experience report is the fact that all this took 1 week of after hours hacking. So the part of the value in all this is that I was able to do this in a very short time because the functional approach to writing interpreters and the functional approach to just changing the types and thereby changing the meaning of the program lended itself very well to this approach. So step one, so let's see how it went. So step one was writing a concrete interpreter. So this one is idiomatic Haskell. First we parse the game data, so the description of a given adventure game, into an algebraic data type. Then the game state itself is represented as a simple product type. So in this simplified version, the only state is the current room where the player character is, and the array of item locations. So this, for each item, it tells you at a given instant which room or that item is, or maybe it's in the player's possession. And all the types are 16-bit integers because that's what the original adventure games used, because the basic dialect that ran on the machines that these games were targeting used 16-bit numbers. And then we have a stack of monad transformers, the usual reader-writer state stack, where the reader gives access to the algebraic data type representation of the game data. The writer collects the string output between each interaction step, and then the state monad, of course, holds the state. And then the main driver of this is a function that, given the parsed representation of a verb and a noun, because in these games the input is restricted to just 2 words, so it has 2 dictionaries. So each game has 2 dictionaries. One is the dictionary of verbs, and the other one is the dictionary of nouns. And then once these are parsed, we pass this pair into a function that runs inside this monad stack and gives us a maybe bool, where basically the maybe bool is the end state of the game. So if it's nothing if the game is still running, and it's like just false if we have lost, and just true if we have won. So we will keep running step with the user's input, and we will print the output string between each step. So basically we put a thin layer of I/O around this pure core. So then the second step was to change. So this one gave us an interpreter that you could interactively play. So then step 2 was using SBV's symbolic type. So SBV is a Haskell library which gives you symbolic versions of, among other things, 16-bit integers. So if instead of an int16 you use an sint16, that means that it could have a concrete value, but it could also have a symbolic value. So the first step in this change was to just change the representation of the state, because if the input is going to be symbolic, that means the evolution of the state is going to be symbolic. So we just replace every concrete value. So in this case, the current room becomes a symbolic int, and the item locations is still an array from non-symbolic ints, because the key, the set of all possible items for a given game doesn't change, only the location. So it's only the array values which we replace with a symbolic version of int. So we do this change, and then we derive the mergeable type class instance for it, and that's an SBV type class that basically means that if we have a fork based on some symbolic conditional, then each branch creates a new state, we can merge these states by merging the symbolic values. And then after we do this change, we can just follow the type errors. So basically, we can keep everything the same and see where it breaks. So num operations just work because SBV implements the num type class for these symbolic operations. Boolean operations need some SBV specific versions because in Haskell the Boolean functions are not overloaded in the result types of like comparison returns a bool, so you can't change it to return a symbolic bool and so on. And we can give mergeable instances for the monad transformers from the Haskell MTL library, because all the monad transformers are ultimately just functions. So for example, in the state monad, state SA is just a function from S to a pair of A and an S. So if you have a mergeable instance for S and a mergeable instance for A, you can make a mergeable instance for state SA, and similarly for the others. And you do have these instances because function types are mergeable if only their codomain is mergeable. So for example, in this slide, I show an example where we can write a new combinator, which is a symbolic version of the monadic when combinator. So symbolic when has a very similar type to normal when, but it takes a symbolic bool as the conditional, and it requires the action to be mergeable, and then it basically does both branches and then merges the result using, instead of using if then else, which would work on bools, it uses ITE, which is the if then else operator of SBV. So it's a symbolic if then else. So that's the one that does the branching and then the merging. And then step 3 was, now that we have followed these type errors and fixed everything by using the right SBV functions and writing symbolic versions of monadic combinators, step 3 was to keep turning the crank, right? So after we do the refactoring in step 2, what we end up with is a step function that looks very similar to the original one, but its input is it's a pair of symbolic integers, so the verb and the noun can be symbolic variables, and the result is a symbolic maybe bool, right? So now what we want to do is want to use an SMT solver to find the symbolic ints that are the verb and the noun input, such that the result will be a symbolic just true, right? So that's because that's what it means to win the game. But of course, we can't win a game in a single command, so we have to keep doing this. We have to keep feeding input, and then we get a new state, and if it's not a final one, then we need to create a new input and then evaluate it, and so on. So SBV provides the query monad, which allows incremental SMT queries. So the way it works is that we can feed the two fresh variables for the verb and the noun and get the end state of the first command. Now, of course, the end state of the first command is not going to be satisfiable because there's probably no possible single line input that would win a game. So we get, but what we do get is we get the end state as a symbolic value, and then we can try solving that. So SBV's query monad allows pushing and popping, so we can basically say, okay, I'm going to make a hypothetical query to the SMT solver, whether the end result being just true is satisfiable. But it's not going to be satisfiable, so we're going to pop the constraint that the end result is just true, because we want to keep going, but we can still keep the accumulated symbolic description of the state, so we can pass it as the input state, the starting state of the next step, by coming up with a second pair of free symbolic variables. And that gives us a new end state, which is again probably not going to be satisfiable, but that's okay because we can keep doing this. So we can abstract this into a function, which the type of which I'm showing on this slide. So we can make a function that, if we have a way of creating these fresh symbolic values, then we can, and we have a stateful computation where the state is some type S, Then if we have an initial state, we can get a list of inputs such that the bool computed in this state is going to be true. So of course, because we have a maybe bool, we're going to change our step function slightly so that we only check whether it's just true. Okay, so with this one, we can keep running a stateful computation symbolically and accumulate the input that leads to the eventual satisfying end state. So after we're done with this, we can realize that the only source of really symbolic values is the input, right? Because the initial state is deterministic and it's concrete because it's driven by the game description. So the only thing that's going to introduce really symbolic values, so the values that are not singleton values, is going to be feeding the input. But that means if the input is really a concrete value, then the end state and the end result is going to be a concrete value, just represented as a potentially symbolic value. So we can recover the interactive mode from the symbolic mode by feeding, instead of free variables, we feed it singleton concrete values, and then we can ask SBV to give us the concrete value, if it's a concrete value, but it is going to be a concrete value, the end result, because there's no other source of non-concrete values. So as a small demo, here's the fourth tutorial game from ScottKit, which is a compiler and interpreter suite for the Scott Adams games. So this one has 5 rooms, and as we can see, the coin, which is the treasure we need to put in the throne room. So we win the game by bringing the coin into the throne room. But to go there, we have to go through a locked door, and the key to the door is in the crypt, but there's also a vampire in the crypt. So we need to get the cross from the chamber before we go to the crypt, because the vampire is afraid of the cross, and then we can get the key, open the door, get the coin, and move it into the throne room. So this solution, the one that I just described, can be found by ScottCheck, which is the name of my program, the one that I've described. So it finds it, which is a 14-step sequence of commands, finds it in 3.5 minutes with no other input from the user. So we just feed it the description of the game with these 5 rooms and the connections and the definition of the vampire and all that, and we get this output. And if we plot the time it takes for each consecutive step, or if we plot the cumulative time to solve the game, we plot it in a logarithmic graph here. Of course, we can see the big problem with this approach, which is that it's going to be exponential, which we can see on this plot, because the branches just keep accumulating, and even just discovering the symbolic values is going to involve more and more binary branches at every conditional in the code. So, and of course, that's where more advanced techniques would come into play, like trying to prune this tree. So in summary, our results is that we took Haskell, a generic purpose functional programming language, and SBV, an SMT solver interface exposing a native-like API. And we took an interpreter written in idiomatic style. And just with small changes to that interpreter to support symbolic execution, like I said, the whole project took just 1 week, and keeping the static phase, so parsing the code intact. So we didn't need to change any of that because that happens before we start the symbolic computations. And we were able to recover the interactive mode but from the symbolic implementation by just feeding concrete values. Future work remains increasing coverage of game scripting features. So the original version just barely supported enough Scott-free features to run just this one game, the tutorial game. And But the thing is that I since then I tried. So if I add more support for more opcodes, right? Like support for more kinds of conditionals or statements in the interpreter, that doesn't slow things down because the game data is read statically. So the structure of the script that the game runs is fixed, right? So just because you have more branches, those branches are not taken, so they don't add up to the branching structure of the symbolic values. So that's good news, I guess. And then, of course, we could experiment with more complicated games. But like the fact that it takes 3.5 minutes to run this very simple example game, the demo game with just 5 rooms, it hasn't exactly made me want to try it on more complex games. But that would be the obvious next step. And I guess at this point, it's time for me to check check if the audience is satisfied with the talk. So you can find the implementation of ScotCheck on the URL you can see on the slide. And I'd like to put a special thanks to Levent Erkok, the developer of SBV, for helping me out with both with questions I had about SBV as such, and also with quick turnaround on bug reports. And of course, I'm happy to take questions. Thank you.